Hey, good morning. This is Chintu Asher here. Today we are going to learn about smoke detection selection considerations. In chapter 17, when we go to section 17.7.4.1.2, the design shall account for the contribution of the following factors in predicting detector response to the anticipated fires to which the system is intended to respond. 17.7.1.7, the selection and placement of smoke detectors shall take into account both the performance characteristics of the detector and the areas into which the detectors are to be installed to prevent nuisance and unintentional alarms or improper operations after installation. There are various other factors which you see on the slide is the plumb and the ceiling jet flows, the ambient temperature and humidity, the ceiling shape and surfaces, the ceiling heights, the fuels and fuel configuration, the ventilation system flows, stratification potential, installation requirements, and also the detector capabilities. Smoke detector design. We go to section 17.7.4.2.3.1. In the absence of specific performance-based design criteria, detectors on the ceiling up to 40 feet, that is 12.2 meters in height, shall be placed in accordance with either of the following. The distance between the detectors shall not exceed a nominal spacing of 30 feet, that is 9.1 meters. There shall be detectors within the distance of 1/2 the nominal spacing measured in the right angles from the walls or partitions extending upward to within the top 15% of the ceiling heights. All points on the ceiling shall have a detector within a distance equal or less than 0.7 times the nominal 30 feet, that is 9.1 meter spacing, or 0.7 s. Why it matters? The higher ceiling can cause smoke cooling, stratification, slow activation. These spacing rules help to ensure reliable early detection even before smoke reaches full ceiling height. To summarize everything, for ceilings up to 40 feet, NFPA gives two ways to comply: 30 feet nominal spacing with boundary rules, or a simple 21 feet maximum design radius. Choose whichever works best for you in the layout. This picture shows a fire generated at the base of the atrium of a hotel. The heat from the fire rises, carrying the smoke and hot gases upward. The rising column is called the plumb. Hot air layer forms below the ceiling. As hot gases collect, they spread out along the ceiling. Over time, a thermal layer forms, shown as the dark swirling smoke layer at the top. When the temperature difference between the smoke and the surrounding air is reduced, the smoke may stop rising further. It becomes trapped and stabilizes at a certain height instead of reaching the ceiling as shown in this picture. This is known as stratification. A typical ceiling mounted smoke detectors may not detect that smoke if it has stratified below the ceiling. The note in the image suggests using a beam type smoke detectors which will detect the smoke horizontally across a space can be installed at or below the stratification level. The exhaust fan shown on the top is positioned above the hot layer used for smoke extraction, but might not be of any help if the smoke never reaches the fan. Why does it matter? Especially important in high ceiling buildings like warehouses, atriums, industrial spaces, where large volume spaces where heat dissipates before smoke reaches the ceiling. Stratification can delay or prevent smoke from reaching the ceiling detectors, leading to late detection and increase in fire risk. To overcome this, we can use beam detectors, we can consider smoke management or ventilation design, evaluate ceiling height and expected fire behavior during the system design. The experiment is taking place in a large, tall, industrial type building. Smoke is being released from a controlled smoke source, likely a test generator. Instead of continuing upward indefinitely, the smoke rises initially, then levels off and spreads horizontally and forming a visible smoke layer below the ceiling. You can observe a clear flat top boundary in the smoke column. This is the stratification level. Smoke stratification is when smoke stops rising and forms a stable layer. This can prevent fire life safety systems from detecting a fire in time. What's happening here in this image? A fire at the ground level produces hot smoke. Smoke rises initially due to buoyancy and heat. At a certain height, it cools and stops rising. The smoke then spreads horizontally, creating a stratified layer. A dashed purple line represents the stratification level. Ceiling mounted detectors may not activate because smoke isn't reaching the ceiling. The symbol at the top with the strike through of the detector shows the failure point. The smoke layer is well below the roof where the detectors are normally located. Stratification is a serious problem in high ceilings. Staircase, shafts, vertical shafts, cold environments, large open industrial structures. If designers don't account for stratification, fire may grow undetected, alarm and suppression response may be delayed, visibility at upper floors can deteriorate rapidly. How to counter this problem? NFPA recommends strategies such as multi-level smoke detection, positioning of detectors below the predicted stratification level, using of ASDs, air sampling smoke detection at multiple heights. Also ensure adequate heat release detection, heat detectors or beam detectors positioned strategically, smoke management, mechanical exhaust that pulls the smoke higher. This slide shows that in tall buildings, smoke may not reach the ceiling detectors. We must anticipate stratification and install detection at different heights or use aspirating smoke detection systems to ensure reliable and early detection. Now this is a different scenario. The fire is located at one level above the ground floor. Smoke spreads sideways at the level instead of rising upward. Only a local smoke layer forms around the fire origin. The ceiling smoke detectors still do not receive the smoke. The detectors positioned lower on the intermediate floors are expected to activate while the topmost detector still remains ineffective. Stratification can occur at any height, not only near ceilings. Smoke may remain trapped in the thermal balance layer of the floor. Detection must be placed within the smoke layer and not above it. Detectors on unaffected floors will not trigger in time. To ensure early detection, use multiple levels of smoke detectors. Avoid relying solely on ceiling detectors installed structures. Consider aspirating systems for layered environments and understand the expected smoke spread at different fire sizes. This slide shows that even small fires can create localized smoke layers that never reach the ceiling detectors. Designing for stratification means placing detectors where smoke is actually expected to travel and not just at the top. Here is what anticipating stratification looks like in the field. We place detectors where smoke actually goes and not only where we hope that it will go. The orange arrows that you see, you have one smoke detector and one beam detector which will detect the smoke effectively. Large atriums like this are a perfect examples of where stratification will occur, so detection must be designed for vertical smoke behavior, not just for ceiling height. Hey, let me check how much we have learned. Let's take a poll. Table 17.6.3.5.1 can be used to correct smoke detector spacing for height. Is it true or false? Yes, it is false. It is for heat detector spacing reduction based on ceiling height. Thank you. Spot type smoke detectors on smooth ceilings. This slide explains how to calculate the radius of coverage R for spot type smoke detectors installed on smooth flat ceiling using NFPA 72 spacing rules. ST is the maximum listed spacing distance between detectors. For smooth ceilings, detectors are spaced in a square grid pattern. The coverage radius must ensure overlaps between detection zones. The diagram uses circular coverage representation, that is the red circles, to show the overlap between adjacent detectors, coverage reaching walls with half SD space margin. Given that SD is 30 feet, we need to calculate R, that is the effective radius of coverage. For a square grid, a diagonal between detector covers the longest gap. Diagonal between 4 detectors equals to SD into root 2. Using this formula, we get the final answer, which is the effective coverage radius R is 21 feet, that is 6.4 meters. This ensures that the spacing does not leave any gaps that smoke might avoid. Even though detectors are placed 30 feet apart, the effective detection radius is only about 21 feet, which is why overlap is essential. For corridor spacing, when a corridor is narrow, smoke movement is channelized. It travels directly along the corridor ceiling, not outward in all directions like in an open rule. Because of this guided path, detectors can be spaced further apart along the corridor length. A typical spot detector spacing is 30 feet. In corridors less than 15 feet wide, NFPA permits spacing along the corridor at 1.5 times, but the diagram shows the visual radius method. From the center line, the radius is still 30 feet. Across the corridor with only 15 feet needed to reach each side of the wall. Overlaps between detectors shall occur. Thus, detectors maintain full coverage without shortening the spacing. A practical rule for corridors would be if a corridor is less than or equal to 8 feet wide, spacing may be extended up to 1.7 times. If the corridor is less than 15 feet wide, up to 1.5 meters of the detector spacing could be used. If it is wider than 15 feet, then we need to revert to the normal SD spacing, that is the grid method. Detectors near doorways. Door leakage and ventilation increases early smoke entry into the corridor. Early warning improves due to natural channeling of the smoke. In narrow corridors, smoke is funneled along the ceiling. NFPA allows increased detector spacing because we can predict smoke travel more reliably. Okay, now let's have a good chat. What is the allowable design spacing for a 30 feet nominal detector spacing? The standard design rule in NFPA 72, allowable design spacing is 0.7 into nominal spacing. So the allowable design spacing is 30 feet into 0.7, that is 21 feet or 6.4 meters. Even though detectors are listed for 30 feet of spacing, the actual design spacing is reduced to 70% of the SD to ensure overlapping coverage and eliminating of dead spots. With a 30 feet nominal smoke detector spacing, NFPA requires a design spacing of 21 feet to ensure full coverage and a proper overlap. Here we see a limitation when a corridor becomes too wide for our extended spacing allowances explained earlier. What's happening here? The corridor which shown is 20 feet. NFPA 72 only allows extended corridor spacings when the corridor is less than or equal to 15 feet. Since this corridor exceeds that width, the designer must reduce the detector spacing to maintain the smoke coverage along the corridor width. The maximum coverage radius for a 30 feet nominal spacing is still 21 feet. So the furthest point can be from a detector is 21 feet horizontally. The arrow in the slide, 21 feet max, highlights this limitation. Because the corridor is wider, detectors must be closer together along the corridor. Cannot use the 1.5 into SD rule here. It must also comply with the standard smooth ceiling spacing geometry. Spacing along the corridor is reduced to 20 to 40 feet depending on the coverage shape. Overlapping radius ensures no blind spots near walls or doorways. Once a corridor gets wider than 15 feet, smoke no longer channels effectively, so we revert to the standard 21 feet design radius for a 30 feet spaced detector. Let's take a condition of joists and beams. If the beams are shallow enough, less than 10% of the ceiling height, and they don't impact smoke spread, we can lay out the detectors just like the smooth ceiling. This is a pictorial representation of what we talked about in the previous slide. Because these joists are shallow, less than 10% of the ceiling height, this ceiling behaves like a smooth surface and we can use the normal spacing. Now this is a different condition. When the beams are deeper than 10% of the ceiling height and are spaced wider than 40% of the height, smoke gets trapped. So NFPA requires a detector in every pocket. Now when the beams are deep but not closely spaced, one side is smooth spacing and the other side is half spacing, we adjust the detector layout only in the direction across the beams. Here what we see is the waffle ceiling. Waffle ceiling create independent smoke reservoirs which delays lateral smoke movement and can significantly delay detection if treated incorrectly. Multiple detectors means early and reliable activation. For waffle ceilings, evaluate beam depth and spacing in both directions and design detector spacing based on whichever rule is more restrictive. If you ask me, you should have one detector in each of the waffle. When beams or joists are located in the corridor that is 15 feet wide or less, NFPA allows standard smooth ceiling spacing because smoke still travels predictably along the corridor. If the room is under 900 square feet, treat the ceiling as smooth, beam obstructions don't matter. Thank you.